Hello students, welcome once again. Hope all are fine. Today we will go for an general understanding of bolts, in-depth various parameters of threads. We will go for an understanding of various types of joints and various failure mechanism of bolted connection. At last we will go for some working example. Now let us understand some technical parameters used in bolted connection. First is the standard clearance hole. Bolt holes are made larger than the bolt diameter to facilitate erection and to allow for inaccuracy in fabrication. Code has suggested some standard clearance as given in table number 19, page number 73. Here, the column number 2 shows the diameter of the fastener. Fastener includes the bolt, rivet and pin. Here in this semester, we will majorly use this standard clearance diameter for our bolt hole. Here, this table number 19 suggests that the 12 mm to 14 mm dia bolts will require a standard clearance of 1 mm. And 16 to 22 mm dia bolt will require a standard clearance of 2 mm, and a bolt diameter of 24 mm will require a standard clearance of 2 mm. A bolt diameter larger than 24 mm will require a standard clearance of 3 mm. Here I have isolated the value of column number 2 and column number 3 in these leaflets. Here the nominal diameter of bolt is represented by dmm. Diameter of hole will be equals to d plus this applicable standard clearance. For example, if we are having a bolt diameter of 16 mm, diameter of hole will be 16 plus 2 mm. This is an applicable standard clearance plus 2 mm. Therefore, the hole diameter will be 18 mm. If diameter of bolt is 20 mm, then diameter of hole will be 20 plus applicable standard clearance is 2 mm. Therefore, our hole diameter will be of 22 mm. This shows that if this bolt diameter is 20 mm, then this hole diameter, it is from here to here, hole diameter will be 22 mm. Second in this series is edge and end distance. The edge distance is the distance at a right angle to the direction of stresses or force from the center of the hole to the adjacent edge. This is your edge distance. If this is the force direction, means if your positive and negative x-axis is your force direction, then your edge distance is measured in y direction. This is your edge distance. This is your end distance. The end distance is the distance in the direction of stress or force from the center of hole to the end of the element. This is the end of the element. This is your end distance. Clause number 10.2.4.2 suggests that the minimum edge and end distance from the center of any hole to the nearest edge of the plate shall not be less than 1.7 times the hole diameter. Mind well, this is a hole diameter and not bolt diameter. In the case of sheared or hand flame cut edges, and 1.5 times the hole diameter in the case of bolted machine flame cuts, saw and planed edges. This means if it is a hand flame cut, your edges are not sharp as that of a machine cut edge. Therefore, the code has suggested a coefficient of 1.7 times the hole diameter for an edge or end distance. Here, this clause is applicable to both your edge as well as for end distance. where the hole are made with a machine cut or edges are cut with a machine cut, which means your edge are sharp than your hand flame cut. Therefore, your coefficient reduces from 1.7 to 1.5 into hole diameter. This is a hole diameter, not a bolt diameter. For example, if you are having a 20 mm dia bolt, then your hole diameter will be 20 plus 2, that is 22 mm. For hand flame cut edges, end or edge distance will be equals to 1.7 times 22, that will be 37.4 mm, and for machine flame cut edges the edge or end distance will be 1.5 times 22, that gives 33 mm. Next is the maximum allowable edge distance, which is given in clause number 10.2.4.3, page number 74 of IS 800 2007. The maximum edge distance to the nearest line of the fastener from any edge of an unstiffened part shall not exceed 12 times T into epsilon, where epsilon is 250 by Fy whole raised to 1 by 2 and T is the minimum thickness of the plate. Next is the tack fasteners. Tack bolts are additional bolts provided to satisfy the maximum pitch requirements of the steel structural members. When a member consists of two elements which is supposed to act as a single unit, then they are connected by tack bolts. They are used to prevent the local buckling in a compression members. We will see this in detail in our subsequent lecture. Here, let's see the codal provision for a tack fasteners. The maximum spacing of a tacking fasteners shall not exceed for a tension member 1000 mm and for a compression member 600 mm. We will discuss this in detail in our subsequent lectures during our example solving. Next is the maximum spacing between the bolt and pitch distance. The maximum spacing between any bolts is given in clause number 10.2.3.2, page number 74 of IS 800 2007. The maximum spacing is the distance between the center of any two adjacent bolts in x or in y direction shall not exceed 32 times the t or 300 mm, whichever is less, where t is the minimum thickness of the connecting plates. Maximum spacing in the direction of force, which is also known as pitch distance. The distance between the center of two adjacent fasteners in a line laying in the direction of stress or force shall not exceed 4 tension member, it's 16 times T or 200 mm, whichever is less. In compression is 12 times T or 200 mm, whichever is less, where T is the minimum thickness of the connecting plate. Below figure is the plan view of a lap joint. This is your edge distance, this is your end distance, and this is your pitch distance. Pitch distance is measured along the direction of stress or force. Here we are having a force direction as positive as well as negative x direction. Therefore, pitch distance is measured in an x direction. This is the pitch distance between the bolts. Next is the gauge distance. The spacing between the adjacent parallel line of the fasteners transverse to the load or stress is called a gauge distance. Again, I would like to repeat the statement. The spacing between the adjacent parallel line of a fastener transverse to the direction of load or stress is called a gauge distance. Gauge distance is measured perpendicular to the pitch distance. Here for an angle section, code has given the gauge distance in the leg of the angles. Here for a single row of rivets or bolts, the whole distance should be C from the corner of the angle. And for double row of rivets or bolts, the gauge distance should be A and B from the corner of the angle as shown in the figure. The value of A, B and C are tabulated in table number 31, page number 168 of SP6 part 1. Let's be familiar with the bolts, screws and washer. This is a typical diagram of a bolt. This is known as threaded portion and this is known as unthreaded portion or a sunk portion. This is the bolt head. This bolt is having an external thread. This is a nut. Nut is a complementary element of the bolt. It is having an internal thread. In this bolt and nut arrangement, bolt is held with the help of spanner and twisting or tightening force is applied to the nut. This is the screw. It is similar to the bolt. It is used for a tapered hole. A screwdriver is used to apply a twisting moment at the head. Here we are applying a twisting moment in the head of the screw, while in bolt and nut arrangement we are providing a twisting force to the nut. This is a particular bolt connection. This is known as washer. Washer distributes the bearing force or a clamping force applied by the bolt on the plate. As clamping force is distributed, there will be a less damage to the plate and head of the bolt. Now let's be familiar with the threading of the bolt. Let us first be familiar with the external thread. This point, the innermost point of the thread, is known as root. The outermost point of a thread is known as crest. In other way, crest is a point corresponding to the maximum material limit. Here we will get a maximum material cross-sectional area, where root is a point corresponding to the minimum material limit. This root will have the minimum cross-sectional area. While in an internal thread, we are talking about this green line threading, not this orange line threading. We are talking about this green line threading. This is an internal thread. In internal thread, we are having the outermost point as root, where the innermost point is crest. Let's be familiar with various parameters and dimensioning of the thread. Measure diameter or a nominal diameter. It is a diameter of an imaginary cylinder which passes through the crest of an external thread. This is known as measure diameter, denoted by small d. It is an imaginary cylinder which passes through the crest point of the thread. While for an internal thread, this imaginary cylinder will passes through the root point of the internal thread. That's an external thread. For an external thread, the measure diameter d corresponds to the maximum material limit. This will give the maximum cross-sectional area. This measure diameter will give the maximum cross-sectional area, where in an internal thread, the measure diameter corresponds to the minimum material limit. Again, I would like to draw your kind attention towards the internal thread, which is represented by this green line and not by this orange line. Here, for an internal thread, the cross-sectional area passing through the cross-sectional area of an imaginary cylinder passing through the root will have the minimum material limit. Minor diameter or core diameter. It is a diameter of an imaginary cylinder which will pass through the root of the external thread. This is the minor diameter or an core diameter, represented by DC. It's an imaginary cylinder passing through the root point of the external thread. While This minor diameter represented by capital DC is an imaginary cylinder passing through the crest point of the internal thread. Therefore, we can say that for an external thread, this nominal diameter or a core diameter corresponds to the minimum material limit. In other way, the cylinder passing through the root point of the external thread will have the minimum cross-sectional area, while for an internal thread, the minor or a core diameter corresponds to the maximum material limit. That is, the imaginary cylinder passing through the crest point of an internal thread will have the maximum cross-sectional area. Pitch diameter. Diameter of an imaginary cylinder which cuts the thread in such a way that the thickness of the thread will be equal to the gap between the two adjacent threads. This is the pitch diameter. It says that this thickness of the thread will be equal to this point. This will be equal. I would like to repeat my statement, that is, for a pitch diameter is the diameter of an imaginary cylinder which cuts the thread in such a way that the thickness of the thread will be equal to the gap between the two adjacent threads. In other way, we can say that this is the thickness of thread, will be equal to the gap between these two threads. This thickness of thread will be equal to the gap between these two threads. Thread angle theta. It is the included angle of the threaded phase. This is an included phase. This is an included phase. This is an excluded phase. We are supposed to measure this included angle of the threaded phase. Pitch. Pitch is the distance between two identical points of adjacent thread and it is measured along the axis of the thread. This is the axis of the thread and the pitch is the distance between two adjacent thread measured along the axis of the thread. This is pitch. Lead L. For a single turn or a nut, the distance travelled by a nut along the axis of the bolt or screw is known as lead. For a single turn, when you give a single turn to a nut or a screw, then the distance travelled in the axis of the thread is known as lead. Now let's talk about the type of bolted joints. The bolted joints are majorly divided into two types of joint. One is the lap joint, one is the butt joint. In lap joint, these two members are overlapped and connected by means of bolt. If we provide single row of bolt, is known as single bolted lap joint. This is a view of single bolted lap joint. This is a plan view. This is a side view. This is an isometric view of an lap joint. This is an overlapping length. This length is an overlapping length. This length is an overlapping length. If we provide two rows of bolt, then is known as double bolted lap joint. If we provide two rows of bolt in this manner, then it is known as double chain bolted lap joint. If we provide these two rows in a zigzag pattern, then it's known as double zigzag bolted lap joint. This is a side view of zigzag bolted lap joint and this is a side view of double chain bolted lap joint. Now let's talk about the butt joint. This is a plan view of an butt joint. This is side or a cross-sectional view of an butt joint. This is an isometric view of an butt joint. In this type of joints,
two main plates are butt against each other and additional cover plate, this is known as cover plate. This is the cover plate. And additional cover plates are provided on one side or on both sides. Butt joints can further be divided into two types of butt joint. It's a single cover butt joints and it's a double cover butt joints. Again, single cover butt joints can further be divided into single bolted and double bolted. In single bolted, one rows of bolts on either side of the connecting plates are provided. In double bolted butt joints, two rows of bolts on either side of connecting plate are provided. Here the number of cover plate is only one. Again, double cover butt joints can further be divided into single bolted butt joints and double bolted butt joints. Here we are providing two cover plates on either side of the plate to be connected. If we provide single row of bolts on either side of connecting plate, then it's known as double cover butt joints with a single bolt. If we provide two rows of bolts on either side of connecting plate, then it's known as double cover butt joints with double bolted. The various mode of failure of bolted joints are as under. They are shear failure of bolt, bearing failure of bolt, tensile failure of bolt, and bending of the bolt. Various plate failures are shear failure of plate, bearing failure of plate, and tensile failure of plate. Out of this, code has recommended various design capacity formula for A, B and C type of failures for bolt and A, B, C type of failures for the plate. While this is an workmanship error, hence this is to be taken care by the site supervisor. First, we will see about the shear failure of the bolt. Plate bolted together when subjected to a tensile force or loads may result into the shearing of bolt. This is the shearing of bolt. In case of lap joint, this is a lap joint where the shearing of bolt occurs at one plane, it is referred to a single shear failure. This is single shear failures. This is your shear plane. This is your single plane. We are having a single plane and bolt gets sheared into two pieces. This is the bearing failure of bolt. When the strength of bolt material is lower than the material of the plate, the bolt will not be able to provide sufficient bearing to the plate and bolt will fail in bearing. This is an indentation of the plate moving towards the negative x direction. This is known as bearing failure of the bolt. Here this bolt material is weaker, or we can say that bolt material is of lower strength than the plate material strength. Then such type of failures occurs in the bolt. This is known as bearing failure of the bolt. Tensile failure of bolt. When factored tensile force, this upper and lower force, this force is applied by this nut and this force is applied by the head. When the tensile force is applied on the body of the bolt, in other way, when the factor tensile force on the bolt exceeds its tensile capacity, the bolt will fail in tension by formation of this necking of bolt. The tensile capacity of bolt depends upon the tensile strength of bolt material and minimum cross-sectional area. As we have discussed earlier, this is an workmanship error and is to be taken care by a supervisor. Now let's discuss about the plate failure. This is the shear failure of the plate. The shear failure of the plates occurs when the shear stress exceeds the shear stress capacity of the plate. The plates get sheared at an angle of 45 degree to the force line. Here this is the force line. This is a bearing failure of the plate. This type of failures is observed when the bolt capacity is larger than the plate capacity. It can be identified by seeing the corrugation on the plate surface. This is the this is the tensile failure of the plate. Here the plates get steered perpendicular to the force direction. This is our force direction. Here the plates get sheared perpendicular to the force direction. Now let's go for an example. Here we are supposed to design a lap joint between two plates 80 mm wide and 12 and 20 mm thick. They are subjected to a factored tensile force of 70 kN. They are connected by M20 bolts of 4.6 grade. Grade of plate is 410 MPa or Newton per mm square. Now let's solve the example. Here the given data are like this. P, that is factored tensile force P is 70 kN. Ultimate stress carrying capacity is represented by FUP is 410 Newton per mm square. Here the grade of bolt is given as 4.6. That means this 4 represents the 100th part of its ultimate capacity. Therefore, FUB, that is the ultimate stress carrying capacity of bolt, is 4 into 100 is 400 Newton per mm square, while 0.6 represents thus yield stress is 60% of its ultimate capacity. Therefore, F5, that's the yield stress, is 0.6 of FUB. That comes out to be 240 Newton per mm square. Now, as we have seen that the bolts are to be designed for shear and bearing. Therefore, first we will find the shear capacity of this bolt. Now, here the bolt diameter is given 16 mm. Therefore, diameter of hole will be equals to D plus clearance. Here from table number 19, page number 73, clearance is 2 mm. Therefore, diameter of hole represented by DO is 16 plus 2 is 18 mm. Now we are supposed to find the shear capacity of the bolt. The shear capacity of bolt is given in clause number 10.3.3 located on page number 75 of IS 800 2007. Here VNSB represents nominal shear capacity of bolt is equals to FUB divided by under root 3 into bracket NN into ANB plus NS into ASB. This is code IS 800. Here the applicable clause is 10.3.3 where we are supposed to find VNSB, where NN is the number of shear plane with threads intercepting the shear plane, NS is the number of shear plane without thread intercepting the shear plane, ASB is the nominal plane shrunk area of the bolt, and ANB is the net shear area of the bolt at thread may be taken as the area corresponding to the root diameter at the thread. Let's see this NN, NS, ASB and ANB in detail. Let's develop the thorough understanding about the shear plane interception and single and double shear. In this figure A, we are having two plates having a tensile force in an opposite direction. It is connected by a single bolt as shown in the figure. Here, this is our shear plane. This top plate moves in negative x direction while this bottom plate moves in positive x direction. This is our shear plane. If this shear plane doesn't intercept the threaded portion. Or in other way, if this shear plane intercepts the sunk portion, therefore NN, which is the shear plane intercepting the threaded portion, will be 0, and NS, which is the number of shear plane intercepting the sunk portion, is 1.0. Here the sunk diameter is given 16 mm. Therefore ASB is the sunk area of the bolt is equals to pi by 4 16 square, where A and B is the net shear area of the bolt at thread, which is measured at the root of the thread, which can be taken as approximately 0.78 of ASB. Figure B represents the single shear. Again we are having two plates moving in two opposite direction. This is the shear plane. If this shear plane intercepts the threaded portion, this is your threaded portion, therefore your NN, which is the number of shear plane intercepts the thread portion, is 1.0, and NS, which is the number of shear plane intercepts the sunk portion, is 0. Here we are having the interception of the shear plane in the threaded portion only, and other A and B and ASB remain same. Again for double shear, let's take an example of 3 plates, 2 moving towards negative x direction and 1 moving towards the positive x direction. Here our bolts cracks into 3 pieces, this piece number 1, 2 and 3. We are having 2 shear plane. This is one shear plane and this is second shear plane. It is observed that both shear plane intercepts the sunk area. The thread starts above the third plate. Therefore NN, which is the number of shear plane intercepts the thread portion, is 0, where NS, which is the number of shear plane intercepts the sunk portion, we are having 2 shear plane intercepts the sunk portion, is 2.0. A and B is the net shear area of bolt at thread, is 0.78 of ASB, and ASB is the nominal sunk area of the bolt. Figure D is also an example of double shear, but here one shear plane intercepts the threaded portion and one shear plane intercepts the sunk portion. Therefore NN and NS both value are 1.0, where A and B and ASB remains same. I hope you have cleared your concept about single shear, double shear, interception of shear plane, and how to derive the value of NN, NS, A and B and ASB. Here, since it is not given that where the shear plane intercepts, therefore we are assuming shear plane intercepts the sunk portion. Here we are having an example of single shear. Therefore here this will be the case number A, where shear plane intercepts the sunk portion. Therefore NN will be 0 and NS will be 1.0, as we have seen here. It's NN is 0, NS is 0. NS is the number of shear plane passes through the sunk. This is the shear plane passing through the sunk area, where we are having no shear plane passing through the thread portion. Therefore NN will be 0 and S will be 1.0. ASB is pi by 4 of 16 square, comes out to be 201.06 mm square, where A and B is the net shear area of the bolt at thread, is 0.78 of ASB, which comes out to be 156.83. Substituting all these values and these given values in our equation to find the nominal shear capacity of bolt. Therefore nominal shear capacity of bolt will be FUB, this is 400, it's 400 divided by constant, that is under root 3, into bracket NN is 0, therefore 0 into A and B is 156.83 plus 1 into this NS is 1 into ASB, that is 201.06, comes out to be 46.43 kilonewton. Therefore, design shear capacity of bolt, that is VDSB, is VNSB divided by factor of safety. This factor of safety gamma MB is given on page number 30, table number 5. Here the value of gamma MB for shop fabrication and field fabrication is 1.25. Therefore, substituting this value of 1.25 in this equation, you will get design shear capacity of bolt as 37.14 kilonewton. Let this be your result number 1. Now we are supposed to find the bearing capacity of bolt, which is given in clause number 10.3.4, page number 75 of IS 800-2007. This is the formula for nominal bearing capacity of bolt, which is 2.5 kb, d, t and fu. kb is the constant which is smaller of E represents the edge distance or end distance divided by 3 times d0, this is the whole diameter, or P is the pitch divided by 3d0 minus 0.25, or FUB upon FU, or 1.0, whichever is smaller is the value of kb. D is the diameter of hole, T is the thickness of thinner plate, and Fu is the ultimate capacity of bolt or plate, whichever is less. Here end or edge distance as per clause number 10.2.4.2 of page number 74. This is 10.2.4.2, page number 74. The minimum edge and end distance from the center of any hole to the nearest edge of the plate shall not be less than 1.7 times the whole diameter in case of shear or hand flame cut edges, and 1.5 times the whole diameter in case of rolled, machine flame cut, saw and planed edges. Here we are assuming hand flame cut edges. Therefore, for hand flame cut edges, it should be 1.7 times the whole diameter. Here it's 1.7 times the whole diameter. Whole diameter is 18. This comes out to be 30.6 mm. This is the minimum edge distance you are supposed to consider. We will consider 35 mm edge distance. Pitch distance P as per clause number 10.2.2 given on page number 73 of IS 800-2007 is 2.5 times the diameter of bolt. Here the diameter of bolt is 16. 2.5 into 16 comes out to be 40 mm. FUB as given in numerical is 400 Newton per mm square. FUP as given in numerical is 410 Newton per mm square. T minimum, that is the minimum thickness of plate, is 12 mm. Now to determine the value of Kb, which is the smaller of E by 3d0, P by 3d0, FUB by FUP and 1.0. E is the edge distance which we have derived here, that is 35 divided by 3 times the diameter of hole, that is 18 mm. That comes out to be 0.648. P is the pitch distance, that is 40 mm divided by 3d0. d0 is the diameter of hole, that is 40 divided by 3d0 minus 0.45 comes out to be 0.491. FUB is 400 mm and FUP is 410, comes out to be 0.975 and 1.0. Out of these four values, smallest is the Kb value. Therefore, Kb value will be equals to 0.49. Substituting all these values in this nominal bearing capacity formula, we get the value as 94.08 kilonewton. Therefore, design bearing capacity of bolt represented by VDPB is equals to VDNPB divided by gamma MB. Gamma MB again is the factor of safety which is derived from table number 5, page number 30. Here the value of gamma MB for both shop fabricated and field fabricated is 1.25. Substituting this value in this equation, we get the bearing capacity of bolt as 75.26 kilonewton. Design strength of bolt VDPB is taken as smaller of VDSB, that's a design shear capacity of bolt, that is 37.14 kilonewton, and VDPB, that is 75.26 kilonewton. Out of these two values, the smallest is 37.14 kilonewton is your bolt value. Therefore, bolt value will be equals to VDB is equals to 37.14 kilonewton. Therefore, number of bolts required will be equals to total load to be transmitted divided by bolt value. This comes out to be somewhere about 1.88. We have to round it about two numbers. These two numbers is capable to resist 70 kilonewton tensile force. Now we are supposed to check the strength of the plate in tension. It is given in clause number 6.3 of page number 72. As per this clause, the design strength in tension of plate TDN is 0.9 of AN FU upon gamma ML, where AN is the net effective area of the members and Fu is the ultimate stress of the plate material. Here AN is the net area in which we are supposed to deduct the whole from the gross area. Therefore, TDN will be equals to 0.9 times AN is the net area. The net area is calculated by deducting the whole from the gross area. 80 is the width of the plate minus 18 is the diameter of hole. This 80 minus 18 gives the net width of the plate into 12. This is the least thickness. We are having two thickness, 12 mm and 20 mm. Least is the 12 mm. Here we are supposed to take the least thickness into 410 is the plate grade divided by gamma ml. This is the factor of safety again given in table number 5, page number 30. This is table number 5, page number 30. Gamma ml is 1.25. Substituting these values, you will get value is 209.63 kilonewton. This is the capacity of plate against a rupture. Since our plate is subjected to only 70 kilonewton force, our plate is safe in tension. Here I have drawn the lap joint connection in which our end distance are 35 mm and pitch distance is 40 mm. Hence, total connection length comes out to be 110 mm. This ends our numerical.
This ends our lecture. In next lecture, we will go for a number of working example. Thank you.